It's over? All right. Good afternoon, everybody. Hope you enjoyed your Saturday morning and you've all recovered from whatever you were up to last night. We have stories, yes. I'd like to introduce here Travis Goodspeed, who we all know, of course, as the Canadian race car driver from Niagara Falls, Ontario. After karting and some amateur classes in Canada, he competed in the British Formula 3 Championship National Class for performance racing in 2003 and finished sixth in his class. He also made 2 starts in the German Formula 3 Championship for the same team that year. He returned to North America and shifted to the Indy Pro Series in 2004, competing in the full season for Brian Stewart Racing, finishing 6th in points with best finishes of 3rd at Homestead and Nashville. He then put his driving career on hiatus to study motorsports engineering and design at the Swansea Institute in Wales. After graduation, he will return to the Firestone Indy Light Series, formerly the Indy Pro Series, in 2009, competing for the Guthrie Meyer Racing Team. He's here today to chat about MSP430s, ladies and gentlemen. Travis Goodspeed.
Howdy, everybody. So, the truthful stuff about me. In 2007, I wrote the first Stack Overflow exploit for the MSP430, which is a 16-bit microcontroller from Texas Instruments. I also reverse engineered a traffic light controller and got in a little bit of trouble over that. 2008, I wrote a reverse engineering tool for the same chip. So given a firmware image, this tool will allow you to identify where functions begin and end. You can do a call graph showing how the program is connected to itself, and then as you identify pieces, you can view them in the larger framework, sort of like IDAPRO, but taking advantage of some of the memory limitations of this chip. Because it's so much smaller, you don't have to use complicated sorting and searching algorithms. You just shoot everything into an SQL table, make queries on it. Worst case, you've got 65,000 rows. So it's never large enough for performance to become an issue. I also did a timing attack on the bootloader of this chip, which allows the password that protects firmware from outsiders to be cracked. I built a physical device for doing this, and then I repurposed the TI EZ430 kit so that I can run my own arbitrary firmware on that device. In 2009, I'm going to do neighborly things, some of which have no practical value, and this lecture covers a lot of that stuff. So first, I'm going to give you masked ROM images from an MSP430. So if you shave off the lid of the chip and you actually photograph what's inside of the plastic, you can see the ones and zeros of its read-only memory. And I'm running a contest to see who can convert an address to a physical location first. If you do this, I'll give you a Hackaday Bus Pirate, which is a universal bus adapter for reading and writing microcontrollers and memory chips and things like that. Then I'll be doing a sort of beginner's introduction to making a board from scratch. So if you want to make your own MSP430 device and you've never made a board before, I'll cover the simple things that you need, like pull-up resistors and the reset pin, that sort of stuff. And then you'll have everything that you need to throw a simple board together that functions. Then for the demo coders among you, I started thinking that a lot of the demo coders are very good assembly language programmers, and they focus on fitting a lot of stuff into a very small piece of memory. Well, that's what's done in advanced microcontroller programming. So I'm doing an example of self-reprogramming for multiplication. A lot of these chips don't have a multiplication unit, so I'll be demonstrating a way by which you can write a function that writes a function to efficiently multiply by a constant. So this is a snail that I found last week on a French Metro card. And when you start taking chips apart and looking at them, you find things like the snail or the masked ROM, which were either put in there as artwork by the designers, as the snail was, or which can be, by their physical properties, can be read just because of the necessity of how they're constructed. The only thing that hides a, that's odd. Oh, I've got 3 open. The only thing that that hides the function of a chip is that it's very small. So with the proper microscope and delayering techniques, you can read pretty much anything. And thanks to Brooke Hill for letting me borrow his lab and hang out with his pets and that sort of stuff. The MSP430 22X4, as I call it, it's the same die shared among the 2254 and the 2274 and a couple of other part numbers. And when you purchase it from TI, even though the part number on the die is the same, they'll cut out some of the features if you haven't paid for them. So if you buy the 54, which has half as much flash memory as the 74, all of the flash memory is still on the chip, but only half of it is active. It's a 16-bit microcontroller. Everything in memory is a 16-bit word in hardware. In assembly language or machine language, you can do a fetch of a byte, and then it appears to be little endian. But internally, every fetch from memory is 16 bits. And then the mass ROM itself has 1,024 bytes. That's a typo. 8,192 bits, which are 512 bits in each of 16 columns. And I'll be providing you with photographs. So if you're the first one to do this, I'll give you a Hackaday Bus Pirate. And if you can also give me a program to generate what the masked ROM looks like from a binary file of the contents of this, then I'll also give you a prototype of the GoodFET, which is my clone of the TI MSP430 programmer. And it's a superior clone, but we'll get into that later. Now this is the master ROM itself. You can see at the top here, these little devices run the data out of the chip. And then each of these 16 columns is composed of bits. This column on the right is the most significant bit. This column on the left is the least significant bit. And a fetch is made from every column at once, because you need to fetch 16 bits at once. This is a larger die photograph of a different part number, but I believe that this region here is the masked ROM. You can identify it because it looks sort of like an Egyptian tablet under insufficient magnification, and it's always taller than it is wide. So the first step to getting these photos is to actually decap the chips. You've got to drop them into fuming nitric acid, which is nitric acid of such purity that it reacts with water vapor and constantly fumes if you have an open bottle of it. And once you do that, you'll get the chip itself with bond wires. Then the bond wires have to be plucked off. The bond wires connect the actual die, which is right about there in the center of the chip, to the pads which are on the sides of the chip. When you drop it into the acid, also under heat, this has to be 60 to 90 Celsius. When you drop it into the acid, the package itself will begin to sort of slop off. And then the longer it slops, the more it fills the surrounding acid, and it makes this brown smoke, especially if you're doing a whole chip at once instead of just eating a hole in the lid, which dissolves less plastic and produces fewer fumes. When the acid turns green, it's spent, and at this point it can no longer etch off of the chip. It's also useful to be able to see the chip at different layers. And while you can remove layers with hydrofluoric acid, you can't put them back on. So I did a quick run of 6 chips, one of which I lost, for getting multiple layered photographs of the same die. And then I could just look at the ROM on each of them and photograph the one that was clearest, that had the least bit of glass on top of it, but which had no bits removed. So I dissolved them all in nitric acid, and then I used hydrofluoric acid, which is Wink's brand rust remover. It's about a 7% solution, also heated. I would bring it up to its boiling point, then remove it from heat, drop the chips in. Then I removed a die every minute. So this chip on the left has been etched the least, second least, third, fourth, fifth. These 2 chips have been etched too much, these 2 too little, this one's just right. So to quickly summarize, use fuming nitric acid, 90% solution at 60 to 90 degrees Celsius. This will dissolve the packaging itself, but it won't hurt the chip. You can leave the chip in here for as long as you like without damaging it. The hydrofluoric acid dissolves the chip itself, so you've got to do a limited exposure. And this will break the chip, so don't expect to be able to run it after HF exposure. As far as taking the photographs go, I started on what I later found out to be the bottom right corner. So this column here is the most significant bit, second most, and so forth. And these little dots are zeros. You can see them exposed here. And it's easy to tell that these are actual bits by counting them. You'll find 512 in each column, and then 512 times 16 is 8,192, which is the number of bits in the program. And then once the bits have been isolated, you can use Photoshop to mark them and then remove the original photo, which is kind of blurry and difficult to read, especially in print, and wind up with something that's very clear and easy to read, or could even be done by simple machine imaging. I mean, just take a bitmap, take a column, run right through. So to read a word, you take one bit from each column, and it will be the same position within each column. So however you find your position within the column from the address, from there it's easy to read the word. You just take the bit from each point. If it's a dot, you have a 0. If it's not a dot, you have a 1, and then you combine them all into a 16-bit word. So this being the bottom right corner, you've got the F bit, the E bit, the D bit, the C bit, the B bit, all the way down to the 0 bit. And the contents of this is a serial bootstrap loader. If you want to program the chip and you either don't want or can't afford a debugger, you can instead program it by the bootloader ROM by twiddling the test pin as you turn the chip on. So you send 2 pulses on the test as you reset the chip. This is password protected. I've broken the password protection on a lot of these chips. And then if you grab my slides online, or if you want to write it down now, these are the beginning words, and these are the ending words, with that one there being the very last word of memory, second to last, third to last, and so forth. And then the addressing, logically, the ROM is composed of 1,024 bytes, which are 16-bit addresses pointing to an 8-bit byte. And they're all even aligned as words. And the ROM itself goes from C100 to 1,000 hex. Physically, though, it's different. You've got 512 words, and every fetch is a word-wise fetch. And then the individual byte is selected by the least significant bit of the query. So the instruction decoder will actually decide whether it's going to fetch, or which half of the word it will fetch. But inside the memory itself, it gives the entire word, and then that's masked off. And there are 9-bit addresses pointing to 16-bit words. It would have been 10, but the least significant one is always 0 because you're always fetching a whole word. And then you've got your offset here. So the challenge is, given an address, can you tell me where it will physically be located? And if I point to a physical location on the ROM, can you tell me the address? Can you tell me which word would be before it, which word would be after it, and so forth? And also, if I give you a digital copy of this ROM image, can you give me a computer rendering, whether it's ASCII art or bitmap or whatever, that accurately shows whether each dot will be in place or absent? So if you solve this, call me on my cell phone number, which is there. You can grab the images from travisgoodspeed.blogspot.com. And that will be fun. So it's an infuriating puzzle. What's the other one? Preview. There we go. Okay. So next I'm going to speak about how to start using the MSP430 as a chip. So if you've been working with the Arduino and you want to move upward to begin making your own circuit boards, There are some things that are a bit more difficult about it, but by and large, it's not nearly so hard as you would imagine it to be. There's no standard hardware. There are development boards, and some people use them, but it's not like the Arduino, where you've got this massive community around you, and everyone's using the same hardware with perhaps a little modification or two. The EZ430 is the most popular kit for this platform, and hardly anyone uses it in practice because the target chip is so small. There's also no simple programming language. There's no common implementation of Forth or BASIC that is in general use. There's no beginner-friendly community. If you don't know what a series resistor is or a pull-up resistor, and you ask for help in the MSP430 forums, quite likely they'll tell you to go to hell and read the manual. And the debugger is closed, both in hardware and in software. But a couple of us are working on that. So the good news is that you'll learn to make your hardware because you have to, and you'll learn to code raw C because you'll have to. You also have to learn assembly language, and you're going to have to read the actual data sheets of the chip. You'll have to understand what special function registers are, what the interrupt table is, how a chip actually works. To do a minimal chip, you can get away with through-hole design, but if you go above the lowest end chips that they offer, you're going to have to learn surface mount soldering. You can prototype your board through batch PCB, or you can use chemicals and a drill. I use a Chinese firm called Gold Phoenix. You just send them $100 and your board design, and they send you back 1,000 square centimeters of board space. And once you have this design, it's very easy to step it up to higher quantities. If you want to start producing these in mass quantities, you just have to go to the manufacturer and write them a check, and you'll get your boards back. For CAD, you can use EagleCAD, which has a free demo version, which is not allowed for commercial applications, which has board size limitations. Or you can use the GNU EDA project, which is more free and all of that fun stuff, but a lot harder to use. This is the sort of board that you'll make on your first attempt. This is the MSP430 in the center. On the left, there's a JTAG cable for programming. On the right, we've got a serial cable that we won't be talking about. These are the LEDs, and here are 330 ohm series resistors for the LEDs. These are necessary to make sure that the LEDs don't burn out the microcontroller by taking too much current. Here, this R4 is a pull-up resistor on the reset pin. The reset pin is inverted, so if it's low voltage, then the chip is off. If it's high voltage, then the chip is on. And if you leave this disconnected, it sort of floats in the middle, and it uses more power than if it's high or low. It's true for all inputs on CMOS. And the chip doesn't work until you plug in the debugger, which has its own pull-up resistor. So you'll wind up with a board that works when the debugger is connected and then doesn't work as soon as you remove it. That's not fun to fix. This chip has internal pull-up resistors on all of its I/O pins, though. So these two push buttons, because they're pulled up internally, they read as a 1 in input until the button is pressed. Then it's shorted to ground, and it falls to 0. Because the resistor is inside of the chip, they don't have to be on the board. If you were to use a 100 series chip or something older than this chip, you would have a pull-up resistor for each of these. Now, a crystal is optional, but I'll be showing you how to make a clock. And inside of a clock, you need to keep regular timing. The internal clock of the MSP430 works very well if it has a reference clock, which we'll be using in this design. And it also works if you don't care about exactly how fast it's running. Because it's a resistor capacitor circuit, it's running within an order of magnitude of what it should be, perhaps within 10%. But if you try to run a clock at that rate, you'll quickly drift, and then it'll be fast or slow or something like that. The pull-up resistor just needs to be very high, because this is a digital circuit. Ohm's law doesn't apply with the pull-up resistor. So it's 47K, but with V equals IR, voltage equals current times resistance, the current is almost zero. So the voltage drop across this is almost zero, even though it's high. So all that this does is make sure that the reset pin can be overridden by a stronger signal. If you never want the chip to reset, you can actually just short it to VCC. The programming port can be a serial port, JTAG, or SPI-by-wire. We'll be using 14-pin SPI-by-wire because it uses fewer pins and it's easier to understand. For this, you just run the pins from the chip to the connector in the right order. You plug in your debugger, and then you're able to debug the chip. And you'll be able to debug the chip before any external components have been added. So you solder the chip to your board, you solder the debugging connector, you plug it up, and then you're able to single step, you can program the chip, you can do all of those things before connecting the rest of the parts. And then the LEDs all have series resistors, and the arrows point toward ground. So this arrow points to negative, this one points up. You can drive the LEDs into the chip or out of the chip. If the arrow points into the chip, have it high on the other end, and then the output will be inverted, which is sometimes useful. And I've never measured it, but I've heard that it's slightly brighter that way. So this is a gift that I made for a friend of mine. It's called the Clock 10. I number each board in tens, just like you would do line numbers in 70s or 80s style BASIC. Then if I make a major revision of this, it'll become the Clock 20. A minor revision will become the Clock 11. This is the programming connector. These are the switches for setting the time. Here we've got LEDs to display the time in binary, and a single series resistor for all of them on the return. This is a 32 kilohertz clock crystal, which is used in wristwatches to keep time. Because it's so slow, it uses very little power. The power of this chip is proportionate to its clock rate. So when it goes into low power mode between the time being checked, it's only counting at 32 kilohertz and waking up every time the counter overflows. And then the chip itself goes here. It's an MSP430 F2013. By TI's numbering scheme, 20x3, or 2013, under the scheme, the first digit after the F describes the family. So this is a 200 series chip. And then the second digit describes how powerful the chip is. The final digit represents its analog features. Does it have an ADC? Does it have a DAC? That sort of stuff. And then the digit just to its left describes a revision of that, so far as memory is concerned or things like that. For the JTAG connector, always pull the reset line high, or SPI-by-wire TDIO for the 2-wire. So the chip is programmed using pins 1 and 7, and then voltage and ground are sent through the other pins. If you have something that is self-powered, such as by battery, you can omit VCC and have a single row of 7 pins. And then because you can eliminate 11 and 13, you can make it still fewer. In practice, designers will do like their own weird arrangement of JTAG pins. And each designer will have his own. And so when you're taking apart someone else's board, you'll find that a lot of the, you'll find that you have to constantly figure out what their JTAG pinout is, and then make an adapter board or wire to test points and ugly things like that. It's also necessary to have, so there's the JTAG connector. And then you need a power supply with a decoupling capacitor. This is just a little capacitor that makes sure that the voltage remains regular. So as the chip is running, it doesn't accidentally fall to too low of a voltage, which will make it skip instructions and do other weird things that are lovely when you're trying to break the chip and infuriating when you're trying to build something. That's the decoupling capacitor here, and then I've got batteries in the left and right of the board. The LEDs will have a series resistor. We went over this earlier. You can see that current will flow in the traditional non-quantum sense out the VCC pin and then back in through the I/O pins. These are the LEDs. And then the switches pull high or low, but the pull-up resistor is inside, so you don't have to worry about them floating. Then the real-time clock is just 32 kilohertz. You can get them in different grades. I should have realized that before I purchased mine. Because they're so low frequency, they don't use much power. You just connect it to the X in and X out pins. If this were a faster clock, if you wanted a 4 megahertz clock or something like that, then you would have to have external capacitors on the crystal of a few picofarads. And that would be in the crystal data sheet or the microcontroller data sheet. So here are the switches. They pull down to ground. Here's the crystal. To program it, you use a compiler, like IR Embedded Workbench, TI Code Composer, or there's a port of GCC. Each one of these compilers sucks for a different reason. GCC likes to make sure that all of the interrupts are handled for you, which is great when you're programming a high-end part, because if you accidentally enable an interrupt that you haven't written a handler for, instead of crashing, the chip will just go to your handler, realize that it has nothing to do, and return. But rather than immediately return, it calls a C function, which calls another C function, which returns. And because of that, you waste a lot of space in your program. Now, this is a constant amount of space, so it doesn't matter if you are using a high-end chip. You're only wasting 16 bytes or 24, whatever it is. But on the MSP430 F2013, you only have 4 kilobytes of flash memory. On lower-end chips, you might have as few as 512 bytes of flash memory, and then it becomes significant. IR used to have inefficient register usage. They since fixed it, but it used to be that if you called one function from another, it would use 2 of the scratch registers for passing parameters, and the other 2 would just sit unused because it was designed to send 32-bit values instead of 16-bit values, and it would use 2 registers for each. And because no one was reading the disassembly, no one noticed this bug for quite a while. They went through 3 major revisions before it was fixed. You also need a JTAG debugger. You can buy the FET UIF from TI for $100, or if you're willing to wire out jumper pins, you can use the EZ430U, which is a JTAG debugger and an MSP430 F2013 in a single package. It's about the size of a thumb drive, and it has everything you need to program and debug the target board. To use it for another board, though, you've got to have this weird 4-pin Olimex connector that's surface mount and rather difficult for a beginner to solder. What I like to do is just heat up the target board, push the chips off of it to get a clean adapter, and then you can run out the pins individually to make an adapter. And then the GoodFET 10 is my own clone of the JTAG debuggers. I took TI's 2 designs, and I fixed their mistakes, and then I combined them. So I use the FT232R USB to serial chip, which is a very easy chip to use from both a software and a hardware standpoint. In hardware, you only need to add a decoupling capacitor and a USB connector to your board, and you have a TTL level serial port. And then you plug it into your computer, and it just works. TI used the TUSB 3410 chip, which requires all sorts of ugly external components and things which aren't fun to work with. And it has all of these reliability issues if the board gets the slightest bit damaged, or if you've got a weird USB host port. It also has kernel issues in Linux that have been plaguing it for 7 years now. The firmware isn't included in Ubuntu under the right name, so you've got to rename it. You also have to add a UDEV entry manually, and you have to do all of this garbage just to get TTY USB 0 up. By switching to the FTDI, all of that can be eliminated. And then this will run either a patched version of TI's own firmware, which of course can't be distributed, or you can run your own firmware on it, and that can be loaded directly over the USB port without a programmer. TI tried that in their design, but they never quite got it working because the signaling lines on their serial port chip weren't connected. So now that this works, you can actually swap from one firmware image to the other instantly. It takes very little time to reflash. So an open source replacement firmware image can be written around this. There's now an open source driver for the FED and the EZ430. So very soon you'll be able to program these chips as you can with an AVR without any proprietary software or hardware. This is the good FET10. We've got pull-up resistors here, and then it talks to the chip being programmed through these pins here, which have series resistors so that they're not damaged by shorting. And this is the FTDI chip. So long as you have that capacitor there, this will give you a serial port to that. You just run the 2 wires, and that's it. If you run if you connect pins 1.1 and 2.2, you can also get the bootloader working. But you've got to hit the reset pin and the test pin, which are up here, in order to enter the bootloader, which is what TI forgot. Now, the architecture itself, this is the part for those of you that write demos. It's a 16-bit RISC chip in which every instruction is 16 bits. Some instructions will be longer, but the extra part is in the form of data immediate words. For those extra words, they're not part of the instruction. The program counter is actually incremented to skip over them, and then they're dereferenced. So the processor just waits a little bit, fetches that extra word, and by the time it's ready to execute another instruction, the program counter has already been incremented. So it's like reading from memory and skipping over it, but it never goes through the instruction decoder. The instruction decoder only sees the first 16 bits. And it's a von Neumann architecture, which means that there's a single memory for both code and data, so we can execute RAM. And you can't do that on AVRs. You can't do that on PICs. You can't do that on a lot of chips. Here are some example instructions in machine code. 0x27FF is a favorite of mine because I spent so much time trying to break around this. It's a JZ plus 0. This will just sit in an infinite loop if the Z flag is set. So if you compare 2 numbers and they're equal, this instruction will spin forever. This is how the bootloader keeps you out if you're not supposed to have access. But because this instruction runs a few thousand times before the chip gets bored and resets itself, through what's called the watchdog timer. Because it runs so many times, you can sit there and you can play with VCC. You can drop it low and bring it high, drop it low and bring it high, and eventually it will actually skip over this instruction and run the next instruction, which is what would have happened if the Z flag were not set. This breaks the bootloader security of almost every bootloader. There we go. Of almost every bootloader ever made. Smart card manufacturers are having a hell of a time defending against that voltage dropping technique, even today. Now, here's an example of a longer instruction. You've got 90B2, which is a comparison of the following immediate word and the address of the word following that. So if FFDE has the value AA55, then the Z flag is set. And this instruction actually precedes that instruction in the bootloader. Now, executable RAM lets you inject foreign executable code through a stack buffer overflow exploit. But I've talked about that enough in other lectures. Here, I'll be speaking about how to use it as a performance hack. Because instead of having to write your program yourself and know everything that it will deal with at runtime, you can just write a program to write the program that you want to run. And this saves you conditionals. Because wherever you have an if statement, you can replace that with either an included clause or an excluded clause. So either you have the body of the if statement or you don't, but you never have to make the comparison each time you run through that loop. This is very useful if you need to shave a couple of clock cycles off of multiplication, such as if you're doing audio filters with the MSP430. It has a good analog chain. So in Circuit Seller number 212, Chris Paskar Venkat wrote this article called Efficient Micromathematics, Multiplication and Division Techniques for Microcontrollers. And he explained how to use Horner's method to write a function for efficient multiplication by a constant. What I'll be briefly sketching out here is how to extend that to have a program write that function for you. So Horner's method is a way of using shifts and successive additions to multiply. So if we want to multiply FF by 3, 3 in binary is 11, which means that we're going to shift it by 2 to we're going to multiply it by 2 to the 0 power and 2 to the first power, which is shifting 0 times and shifting 1 time. And then we'll sum them. And if you have variable factors, I probably got a couple of these numbers wrong, but they're right in the order of magnitude. You've got to do lots of shifts, and you've got to do lots of conditionals. And then the conditionals will decide whether or not you want to perform an addition. So just keep shifting the number, and if you find a 1 in the factor that you're multiplying by, then you add. You can also multiply a variable by a pre-chosen constant. In that case, we only have to shift this number, and we only have to add once. So if you were to write a function to multiply anything by 3, it's very easy to do. Multiplying by n is rather difficult, especially if you don't have a hardware multiplication unit, which many of the chips in this family do not. So to take it a bit further, if we consider Venkat's method as doing it at compile time, how do we do it at runtime? Our goal is to make this function, create mult, that takes a pointer to memory and a constant, and then it writes a function for multiplying by that constant, such that the two multiplied together are the same as just mul of the non-constant factor. So if you're doing it conditionally, and you were to unroll everything, you would just bit mask R15 to look at its least significant bit, and then you would add if that bit were high. Then you would shift 15, which contains one of the factors, to the right, and you move 14 to the left. 14 is the one that you're successively adding. 15 is the one that tells you whether or not you add. And then you do this for each bit of the number. If you're just doing it by 3, you'd just add the two numbers together, and then you'd shift, and then you'd add the two numbers together. This being so much shorter, a machine can do it. So the idea is that you take, you just need 2 assembly words, so you just define them as constants. Instead of doing ASM add, you just do 5E 0C. And with all of this pre-assembled, the program becomes ASM add, ASM shift, ASM add. So to multiply by an arbitrary value, you just cycle through R15. This should be bit masked to check the least significant bit. But anyways, you just rotate R15 off, and then you append an addition only where it's actually used. But you append a shift for each one. And then if you do this, you've just dropped all of your conditional statements. You've dropped all of your jumps. And a condition takes 3 clock cycles, because you've got to do 1 for the comparison and then 2 for the jump, whether or not the jump is taken. This drops all of that out. You've just saved 3 clock cycles times 16 bits. You've got saved 48 clock cycles here. And you can do this, you can optimize it further. There's no way to shift by an arbitrary value on the MSP430, but you can drop off the unused shifts at the end. So you can make an optimization routine that runs through and puts the return statement in the right place. I think I've run out of time, and I've done a lot of crazy subjects here, but I hope you enjoyed it. So I do have time for questions. Do any of you have them? Yes. Yes, I used a friend's microscope in Texas. You need a very large one with very high magnification. Then you just zoom into the chip at the right spot. You'll see it in a blurry form without delayering the chip. So all you need is nitric acid, and if you're patient, you don't need terribly pure nitric acid. You can have like a large jar of the weaker stuff, and as long as it's heated, it will eat through the chip. If you're impatient, you need very pure acid, and it needs to be very hot, and then it will just dissolve the packaging in front of you. I have pictures of my Flickr feed of the entire process in the lab, and a bit of the lab equipment that I didn't get to get into here. There's a cat whisker needle that can be stuck inside of the chip. It's moved by micropositioning knobs, just like a microscope is. And this was snaked out over a board, and then we stuck it into a chip that was still running. We were able to capture one of the lines of a clock and actually view the clock on an oscilloscope, and we could halt the clock by pulling that low. Yes? Yes, it was quite neighborly. Anyone else? Yes?
So what are some of the techniques that they could use to protect against voltage dropping?
You can have two different circuits that, I'm not familiar with how they do it in practice, other than that the methods they do in practice have a lot of thought put into them and that they don't work. If I were to do it, I would have two different circuits which accomplish the same thing that were constantly running. So you might have a ripple carry adder and another type of adder, like a carry look-ahead adder. And then you have these two generating numbers where the result ought to match on each clock edge. If they don't match, then like reset the chip or destroy memory or those sorts of things. The problem with those techniques is that if there's ever a glitch for reliability reasons that has nothing to do with an intentional voltage glitching attack, then I've just nuked a customer's chip or 500 customer chips or 5,000 customer chips, and that's usually not worth the defense cost. I buy the MSP430 because it's a reliable chip and it's easy to program and it's easy to debug. If it starts breaking, I'll move to another chip, and I won't give a damn what security that buys me. So if you're trying to come up with a good defense against voltage glitching, you need something that has no false positives, and at the same time, you need no false negatives, because if you have a single, if you have a false negative of a reachable probability, then the chip can be broken. So it's a lot harder of a problem than it seems at first to defend against this. A capacitor and a resistor inside the chip will also help. But yes?
I got a question. Is the stuff that you're working with the wireless, do you see any of the wireless or access points using these type of chips?
Okay, so he's talking about the 802.15.4 chips and the vendor-specific clones of those that I've worked with in other lectures. I have seen them in deployment. They're usually in industrial areas. There are a couple of hotels in Vegas that use them. Next DEF CON might be interesting. If anyone's up for a road trip, let me know. Yep. Anyone else? All right, thank you.